We have some time for questions. Please.
Yeah, thank you for your interesting talk. I have a small technical question about the beginning when you introduced a free Pfefferman system. You have this equality only for closed terms. Why only for closed terms? Why not for all terms?
Well, what would it mean for one variable to be equal to another variable? You could universally quantify them, if you like.
But you may have terms which contains constants and variables. But yes, to fully exclude them...
If I have a variable x and a variable y, when would I say they are equal? I don't know what that means. I mean, you could say they are equal... What? Yeah, I don't know.
Well, you do through inequational logic. You also have expressions x equals y.
Yeah, but so they can be true or false depending on how you instantiate the variables.
Yeah.
But I want to say that terms are equal or not. If they're variables, it depends.
Yeah.
So that's why I had only for closed terms,
okay,
because then I have a definite answer whether they are equal or not.
I see.
I mean, you're right, I can still have equations with terms with variables, but... Yeah.
But did Pfefferman do it already that way?
I think so, yeah.
Yes? Oh.
Yeah, well, I think so, yeah. Yeah.
Yes, Andy.
I always found the partiality aspects of partial combinatorial algebras to be a real pain in the backside, but leaving that aside, does anybody, I mean, a natural thing to consider when you're looking at morphisms would be partial functions between PCAs rather than total ones. That would somehow fit more in the picture. Does anybody sort of studied partial embeddings? Or?
No, not that I'm aware of. I like the partiality because it includes more examples. So it increases our stock of examples. And like Klee's first model is certainly much more natural with a partial application than with a total one. So that's one reason for me. I'm a computability theorist, so you will understand this first model is dear to my heart because I work in it daily. Yeah, it's a good question. I don't know if that has been looked at. I don't know any reference for that.
So it is known that the comprehension and extensionality lead to problems like Russell's paradox. I'm wondering, in this result here, how does that relate to such an observation?
I don't know. It's interesting you mentioned Russell's paradox because it does play a role also in this context. Maybe people have forgotten, but when Church introduced the lambda calculus, originally he intended it as a foundation for mathematics, so he included logic. So it was not only the function application formalism, but also logic. And if you combine the two, it becomes inconsistent because you get Russell's paradox. So this is sort of interesting because twice in not too long period, Russell's paradox killed a formal system. So when it was pointed out to him, of course, he immediately ditched the logic part and kept the lambda calculus part, which we now all know. Yeah, I don't know of any other remark to make about that in this context, but yeah, so it sort of hovers around here.
Other questions?
Thanks. Thanks for the interesting talk. So John Longley motivates his applicative morphisms, which I think at some point got renamed to simulations, which makes a lot of sense, because he relates them to realizability theory and category theory. There is a correspondence between simulations and functors, between realizability models. Are there sort of maybe presumably of a different kind, reasons why you know that the weak and the strong embeddings are, so to speak, the correct notion to study?
Yeah, that's a good point. I mean, so there are these various ways to look at these mappings, and as you say, the applicative morphisms. I thought that in the book by Longley and Norman, they were still called applicative morphisms. But okay, so simulation is also a good word because that's exactly what it means. It means that the PCA-B that you map into can simulate the original one, so that's good. It's certainly a natural notion, and I guess in the category. So yeah, includes that in his book, because in the categorical context it makes sense to look at these mappings. From an algebraic viewpoint, the weak and the strong embeddings certainly make sense. So, and as I say, they existed before in the literature. I wouldn't claim that any of these is the right one. I think they're all interesting for each has their own reasons to be interesting, so to say. It would be interesting to see. So I've been studying the embeddings at the level of the PCAs, sort of purely as algebraic structures. Of course, you can ask follow-up questions. What if you have an embedding of PCAs of each of these kinds? What kind of consequences does that have for the structures that are built on top of them? Yeah, that's I don't know. That's a good question.
Okay, two more. Well, obviously, Jaap should have a chance to ask a question.
Yeah, Bas, thank you very much. I have maybe a stupid question. When I think about the completion of a PCA, right? I take the diagram of A. Maybe I express the application relation as a ternary relation, right? So it can take the diagram of A together with the axioms for K and S, which are simple sentences, and the statement that application is total. Now, in the case of a non-completable PCA, this is an inconsistent theory. So there's a finite part of it which is inconsistent by the completeness theorem. Can you imagine what kind of finite parts are inconsistent?
Yeah, I think we have to get very syntactical here. So this counter example of Klopp from the 80s constructs something horrible in a purely syntactic way to make sure things go wrong. And the proof is, pages of sort of arbitrary looking things with expressions with K and S in it.
Okay.
So it's very hard to extract any informal idea out of it.
Let's hope it's not an example of long analysis, wrong analysis.
No, well, we know that, yeah, so, okay. I'm not, so we had other examples as well. Like I say, we know that if you have an extensional PCA, you also get, those certainly exist. But yeah, I don't know what the answer to your question is for those examples. That would presumably be some different argument. But you're right, it should go wrong at some finite level. I don't know. It's probably some very complicated expression. I don't know.
Okay.
They're not very natural, these things. I think all the natural examples of PCAs I know, they all have completions. So in that sense, they are sort of unnatural.
About these, about the set of all partial computable unary functions, can you give a characterization of what kind of combinators don't exist other than S?
No, I only know, so K is no problem, but so S doesn't exist. I just, to show that something that doesn't give a PCA, I only have to show S doesn't exist. So I'm sure other things also don't exist, but I have no particular reason to be interested in other combinators. So it's enough to have one of K and S not exist. So, and it's of course the S combinator which gives the problem, because K is just projection, so that is easy.
Thank you. Any more questions? I'll ask one then. Have you thought about the ordered case? So when you have ordered PCAs?
Yes. I even had some slides about that. So in the part which I didn't discuss, the computable model theory part, there was an interesting question about the isomorphism problem for PCAs. So what do people do in computable model theory? First of all, they do model theory, but they first restrict their attention to computable structures, and then they ask what the complexity is of classical things, like how difficult is it to see that two linear orders are isomorphic, or two vector spaces, or two other whatever spaces you're interested in. And typically for various basic kind of structures, this turns out to be very hard because even if you have two computable structures, the isomorphism may be very complicated. So this is typically gives you things that are at the level of sigma 1, 1, so higher than the arithmetical hierarchy. With Katja Fokina in Vienna, we looked at this isomorphism problem for PCAs. We didn't do it for computable PCAs because they don't exist. So we went one level up. We do it for computably enumerable PCAs. But we couldn't, so we had some partial results, but we couldn't answer the final question whether it's really, so sigma 1 is an upper bound, but we couldn't prove it's complete. So what do you do in mathematics if you try to prove a theorem and you can't do it? You prove a related theorem that you can prove. So we couldn't do it for the PCAs, so we went to this order PCAs that you mentioned, which occurred in the, so they were introduced by Jaap. That's why I also had some slides about them here. And they were studied in the recent thesis by Jetse, who was also here, I think. There he is. So we could solve the problem for these order PCAs. I think Jetse calls them just PCAs because his whole thesis is about the order PCAs, but it's confusing because it makes a rather big difference, order PCAs. It's a much larger class, which is the reason that we could prove that it's sigma 1, 1 complete, the isomorphism problem, because it includes these linear orders, so we could just import the results, the classical results from Harrison from the 60s, that isomorphism problem for linear orders is sigma 1, 1 complete. So it doesn't really give a clue about the isomorphism problem for the real PCAs, but thank you for mentioning the order PCAs, because I wanted to talk about that a little bit, but time was up, so I had to skip that part.
Now you've also discovered that they're way nicer.
Okay, any final last question? No? Okay, then let's thank Bas again and let's have a break.